All right. Hello, everyone. Hope y'all are well. All right. So the goal, as usual, is to just relax and do some math together, have a good time. And so today I wanted to think about this rather curious thing here. So it's a very odd little, what seems like a coincidence. You know, you have 0 to the 0 plus 3 to the 0 plus 5 to the 0 plus 6 to the 0, all the way to 15 to the 0, and so on. And then it goes all the way up to cubes. So essentially you're splitting the numbers 0 through 15 into two groups, right? So you can imagine the numbers 0 through 15. Hold up, I lost my stylus. Where'd it go? Well, I cannot write until I find my stylus. Uh-oh, this is embarrassing. So, let's see. Where is my pen? Well, how exciting. So for those of you just joining me, I'm looking for my stylus. Okay, I found it. Oof. Okay, anyways. So the idea is that you have the numbers 0 through 15, right? So you have like 0, 1, 2, 3, all the way through 15. And then you're dividing these numbers into two groups, right? So when you divided them, it turns out that 0, 3, 5, 6, 9, 10, 12, and 15 ended up on one side, and the remaining numbers ended up on the other side, okay? And you know, then you have this property where if you take powers of them and add them, it winds up being the same on either side. And so the first question to ask is, how exactly is this split being made, right? How are we deciding which numbers end up on one side versus which numbers wind up on the other side? Well, it turns out there's a very rather curious algorithm that you use to decide which numbers wind up on one side versus which numbers wind up on the other side. So here's the idea. It's very simple. You start out with, you write 0 down, okay? Then the next thing you do is you take everything that you've written so far and you turn the zeros to ones and you turn the ones to zeros, okay? So this 0 becomes a 1, okay? Now again, take everything you've written so far and flip the zeros to ones and the ones to zeros. So then you would take everything I've written so far and flip it. So you get a 1, 0, because you flipped the 0 to 1 and 1 to 0. Now take everything you've written so far and flip the zeros to ones and the ones to zeros again. And so then this would become 1, 0, 0, 1. Okay? Now take everything that you've written so far and flip the zeros to ones and ones to zeros again. So this would become 1, 0, 0, 1, 0, 1, 1, 0. Okay? And you can do it again. And what I'm trying to tell you is you're actually using this sequence to decide what terms wind up on one side. So on which side. So imagine you're writing all the numbers 0 through 15 above these numbers. So for example, I can put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? And basically, the things that have a 0 underneath them end up on one side of the equation, and the things that have a 1 under them end up on the other side of the equation. So the way that you're making this split is as follows. So the things with the ones, the things with the zeros below them are, again, 0, 3, 5, 6, 9, 10, 12, and 15, okay? And again, the things with the ones underneath them wind up being 1, 2, 4, 7, 8, 11, 13, and 14, okay? So this algorithm is what you use to decide what ends up on what side. Yeah, I know, right? Hello, Ken. Nice to see you again. I hope you're well. So let me know if you understood how this particular sequence is constructed, and then how this sequence is then used to decide which numbers wind up on either side of the inequality. So if you missed it, you write 0 down. So the sequence starts with a 0, and then you take everything you've written so far, and then you bit flip it. And then you just do that over and over again, and that's how you get these sequences. Now, by the way, I do want to point out that you can stop this process at any point, and it still winds up working. So for example, let's say I decide to stop this process. So you start with a 0, bit flip the 0, you get a 1. Then bit flip the 0, 1, you get a 1, 0. Then bit flip the 0, 1, 1, 0, you get 1, 0, 0, 1. Okay? And let's say I decided to stop right here. Okay, let's say this is all that I decided to do. And then my numbers are 0, 1, 2, 3, 4, 5, 6, 7. Okay? Then on one side would go 0, 3, 5, 6. And on the other side would go 1, 2, and 4, 7. And then the claim that I'm making here is that, 0 to the 0 plus 3 to the 0 plus 5 to the 0 plus 6 to the 0 equals 1 to the 0 plus 2 to the 0 plus 4 to the 0 plus 7 to the 0. This should not be surprising, first and foremost, because it's easy to prove that in such a sequence, there's going to be the same number of zeros as there are ones. Hopefully that's not too shocking. And so the first thing is just saying that the number of terms on one side is equal to the number of terms on the other side. So this piece of it should not be particularly shocking, okay? And then the next one is saying that, of course, 0 to the 1 plus 3 to the 1 plus 5 to the 1 plus 6 to the 1 is equal to 1 to the 1 plus 2 to the 1 plus 4 to the 1 plus 7 to the 1, which is, of course, saying that the sum of the terms in one piece of the partition is equal to the sum of the terms on the other side of the partition, which is, of course, I assume, or at least I hope, also not particularly surprising. Right? And okay, so far so good. This one's like a little bit more surprising than the first one, but it's also not too hard to prove. But of course, where things start getting interesting is in the next one. So the next one would be 0 squared plus 3 squared plus 5 squared plus 6 squared is equal to 1 squared plus 2 squared plus 4 squared plus 7 squared. Okay. Now I'm going to open a calculator in case you don't believe me, because once again, this is fairly shocking stuff. So also, please let me know if the music is too loud. Let's see. So I'm just opening Mathematica really quickly. Okay. So you have these two sequences, for example, 0, 3, 5, 6. So you have 0, 3, 5, 6. And you can square all of these and then total them. And you would get 70, okay? And then the other side, you have 1, 2, 4, 7. So 1, 2, 4, 7. And you can square all these and total them. And you, again, get 70, right? Again, pretty shocking stuff. And just to verify that the original claim I said is indeed true, you can take, let's see, 0, 3, 5, 6, and then I'm going to add in 9, 10, 12, 15. And you square them all and you get 620. And then, let's see. 1, 2, 4, 7, I have to add 8, 11, 13, 14. 8, 11, let's see, 13, 14. Another 620. Interesting, right? But of course, the claim is that this will also work if I cube both sides and add everything. So I can just do a cube and cube. So on this side, you get 7,200, and this side, you also get 7,200, okay? So the idea is, of course, if you have a sequence of length 8, right, it'll split into two sequences of length 4 if you do this recursive process, right? So sequence of length 8, 0 through 7, splits into two sequences of length 4. That's 0, 3, 5, 6, 1, 2, 4, 7. And you just see 4 is 2 squared, right? So basically all the powers up to 2 will work, of course. And so implicitly, I'm also making the claim, for example, that if you do for example, let's say I decide to do this process for a sequence of length 64, right? So if I do it for 64, I mean, it's going to be massive. It's going to be a huge thing. But, I do this process again. So, 0, 1, then 1, 0, then 1, 0, 0, 1, then 1, 0, 0, 1, 0, 1, 1, 0. And then I do my bit flips over and over again. The fourth power, it does actually fail. That's a very good question. So I'll show you here. So this is 88,388, and this is 89,924. So it is indeed true that it fails for the fourth power if you try to show they're equal to for the fourth power. But what I'm trying to say, or like at least what I'm trying to indicate, that there's a deeper thing going on here. So for example, you construct this sequence by recursively bit flipping, right? And my claim is that even if I do this one more time, the pattern will continue. So for example, this is a length of 16, and then I can bit flip all of these to get a sequence of length 32. So this would become 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, I believe. So that should be a sequence 1, 4, 4, 4, 4. So that's 16. And then 4, 4, 4, 4. Yeah, so that's 32. So you can use this, for example, to divvy up the numbers 0 through 31 into two groups, right? And the claim is that for this group, the 0th power sums will equal, the first power sums will equal, the square sums will equal, the cube sums will equal, and the fourth power sums will equal will be equal for this particular split. So let me know if that makes sense. It's kind of insane to think about. So just so you believe me, in case you're skeptical, I thought it'd be worth it to just program this very quickly and get the recursive sequences, do the splits, and just show you that what I'm saying is not nonsense here. These are some very interesting patterns here. So by the way, this sequence that starts out, the sequence that goes, these binary sequences that I've been writing down, right? Or these bit sequences that I've been writing down. These are called Morse sequences, in case you want to look them up. Though they've been discovered by a number of people. Like a number of people have discovered them, a number of people have worked on them. So I don't think it's just a Morse who should get credit for it, but like a large number of people have thought about and worked on these sequences. And they have a lot of really, really interesting properties, some of which, I'd like to go over and see what happens. So in any case, you have this. And so what I'm going to do is I'm going to try and get my computer to produce these for me, just so it's more convenient. So what I'm going to do is I'm going to write a piece of recursive code to give me the Morse sequence of length 2 to the n. So this is going to equal, so I'm writing this in Mathematica. You can, of course, do this in any language, though Mathematica is good for writing like really quick code snippets that work in this situation. So I'm just going to define this recursively. So if, n happens to be 0, just return the list that only has 0 in it. Okay. Otherwise, concatenate the previous sequence. So this would be n minus 1. And the bit flipped previous sequence. Okay, so I'll put these in separate lines so that it's clear what's going on. So this is if n is 0, do this, otherwise do that. Now, what this will do is it'll make a list that contains the first list and the second list, and we don't want all the parentheses that will result from that, so I'm just going to write the word flatten. So flatten is a bit of code in Mathematica that gets rid of all extra parentheses, thereby flattening the list. And so this is my piece of code. Okay, so for example, now if I ask it for sequence 0, it should just give me 0. If I ask for 1, it gives me 0, 1. If I ask for, 5, it should give me a list, a bit list of length 32. That's exactly what we want over here. So let me know if that makes sense. Just a quick bit of code to get the Morse sequence of length 2 to the n in Mathematica. Okay. So the input here is n basically, and you get a sequence of length 2 to the n. So hopefully this makes sense. I'm not I'm not blowing anyone's mind here with this crazy programming. All right. So now we would like to use this to kind of partition 1 through 2 to the n, I'm sorry, 0 through 2 to the n minus 1 into 2 separate lists. And then we want to check that the powers are going to equal on either side, basically. So how are we going to do that? So if you were working in Python or something like that, you can actually use a list of, like an array of zeros and ones and input it into, use it as kind of like the input to another array, and it will only give you the positions that where the ones are. And then you could do 1 minus that and get all the elements that where the zeros are, which is kind of interesting. But there's actually something interesting you can do in Mathematica, which I'm not sure how to do in other languages. It's called I'll write this down. It's called a sow and a reap. And don't worry, I'll get back to the math in a second. I just think this stuff is interesting too. So this is called a sow and a reap. And the idea is that if you're doing any computation, right? Let's say you're doing any long computation in like whenever. So this is a long line of code. In the middle of that code, if you see something that you like, you can type the command sow, and you can think of this as like planting a number, okay? And then outside of the loop, you put a reap. And basically, when this code is done, it just looks at everything you've sown and then collects it into a list where the reap is. And so that's what I'm going to do, I think. Not that there aren't easier ways to do this. I just think the sow reap is kind of interesting. So I'm going to use this to kind of plant the seeds that I want from this list and kind of reap them at the end. Okay. So far, I hope everything is clear. And if you're joining now, please feel free to ask me any questions. Also, I think the music has stopped for some reason, so I'm just going to keep it playing. So, all right. Now, let's actually do what I said. So I want to divide the list from 0 to 2 to the n with yield and next. I'm not sure it's completely analogous, but let me know. Let me write it down, and then you can let me know if it's the same. So basically, I want an to be everywhere you get a. So everywhere you get a 1. So this is reap. I'll use a for loop, not that it matters. I could have also used a table or something like that. So should we try a table? So table, let's go I from 1. Actually, let's do I from 0 to, no. I want all the list elements. For 1 to 2 to the n. And then let's see here. So if, let's see, sequence n evaluated at I is equal to 1, just, actually, I don't want a table here. I want a do. Okay, so just to sow the number I. Okay, that should do it. Let's see if this works. So let's try A2. Yeah, that worked. I don't know why Mathematica inserts all these like parentheses. So it worked, but it inserted like a bunch of extra parentheses around. So let me just double check again. So for example, A4, yeah, this is exactly what we want. So 2, yeah, 2, whoa. Wait, what? It's... Wait a second. Oh, I need to do... Let's try this again. Wait, oh, sorry, so I minus 1. Sorry, my indexing is off. Okay, 1, 2, 4, 7, 8, 11, 13, 14. Okay, perfect. That worked. Okay, so I want to get rid of the null and the thing, so I'm just going to say, you know, I just want the internal list, so I'm going to write 2, 1 here. See if that worked. And so A4 is going to be, yeah, 1, 2, 4, 7, 8, 11, 13, 14. So let me know, Ken, if this is actually similar to Python, yield, and next. I actually don't remember how to use generators in Python, so do let me know. And so I can also define bn similarly. And bn will be just the same thing, but I'm only showing the things where I is equal to 0. Hopefully this works. Let's see. B3 is 0, 3, 5, 6. A3 is 1, 2, 4, 7. Okay, perfect. So 2 cubed splits into 0, 3, 5, 6, and 1, 2, 4, 7. B4 is 0, 3, 5, 6, 9, 10, 12, 15, right? And A4 is 1, 2, 4, 7, 8. Okay, okay. So now, so now we can verify the claim that I made earlier, which is that you can, take powers of these and add them, and it'll be equal on either side. So for example, I can take A4. Well, we already did A4, I guess. Let's do like A6, right? To the 4th power and total it. And you get that number, for example, and you could take B6 to the 4th power and total it, and you get the exact same number. It's kind of insane, right? So A6 is, these are the numbers we are adding, and B6, these are the numbers that we are taking the 4th powers of. And the same thing will be true if you take 5th powers. So for example, you take 5th powers here, total them, and 5th powers here, and total them. You get the exact same number on either side. So there really is something quite powerful and sneaky going on here, right? So what exactly is it that is going on? Let me know if there are any guesses as to what is going on here. Just give me 1 second here. All right. Let's see here. Okay. So yeah, let me know if there are any guesses as to exactly what is going on here. All right. So now I want to tell you about another really interesting property of these lists, which is what happens when you take sums of elements, pairwise sums of elements in these lists. So for example, B4 is, let's do B3 and A3. Actually, let's do B2 and A2. Okay. B2 is 0, 3, A2 is 1, 2. So B2 is, 0, 3. A2 is 1, 2. Now here's what I want you to do. I want you to consider a pairwise sum of these elements, okay? So what is that going to look like? So for example, don't ever add the same number to itself. But for example, here you can look at 0 plus 3, and notice you get 3. This is the only way in this case to add 2 distinct numbers. But notice you can also add 1 and 2, and you get 3 in this case. Interesting, right? Let's do it for something more complicated. So for example, let's do it for the lists of elements that occur over here. So you have 0, 3, 5, 6, 9, 10, 12, 15. Okay. And now you have 1, 2, 4, 7, 8, 11, 13, 14. Okay. Let's take a look at all of the pairwise sums you get in this list. So for example, if you add 0 to all of these, you would get 3, 5, 6, 9, 10, 12, 15, right? Actually, this is too much to like do in my head, so I'm just gonna cut this in half. Okay, look at all the pairwise sums you get in these two lists separately. So you would get 3, 5, and 6, and then you would get 8, right, from adding the 3 and 5. And then you get 11 from adding the 5 and 6. And then you would, what else is there? The 3 and the 5. Oh, the 3 and the 6. You also get a 9. Okay? So these are all the pairwise sums you get by adding distinct elements in this list. Now let's take a look at what pairwise sums you get by adding all distinct elements in this list. Again, you get 3 from the 1 and 2, 5 from the 1 and 4, 8 from the 1 and 7, 6 from the 2 and 4, 9 from the 2 and 7, and 11 from the 4 and 7. Huh. Okay, so you have, notice that as sorted lists, these pairwise sums are actually equal to each other. So, you know, this list is the same as this list. This is another really curious property of these sequences, and I believe this was only proven in the 60s, believe it or not. So this as well. And so if you don't believe this, you can ask. So for example, I can ask the calculator to compute all pairwise sums of A6, for example. So it would be like do table like AI plus like AJ, where, for example, J goes from 1 to I minus 1, and I goes from 1 to, what would it be? It would be like, also I need to be careful. So this would be, we're doing for A6, right? So I would go from 1 to, I guess, 2 to the 5. Okay, and then I also want to flatten this to get rid of any extraneous parentheses, and I also want to sort this. So, oh, I did something bad. I need to abort the evaluation. All right, so what did I do that was so bad? All right, let's try for 5. Maybe it's just not happy with me. Okay, yeah, I think that was too much. I think there should be a 9 instead of a 7 in the second list. Where are you? I'm just curious, so are you talking about this list down here? Oh, it's just my handwriting, I'm sorry. This is supposed to be a 9. It just looks like a 7 because I have atrocious handwriting. So I hope, okay, let me get rid of this here and write a very fine and pronounced 9. Okay, there you go. Sorry about that. So, any case, these are all the pairwise sums obtained from A5, for example. And we can do the exact same thing for B5. Let's see what happens. Literally the same list. You see that? Let me, there you go. The exact same list of pairwise sums. Interesting, right? So, kind of wild, right? What is going on here? Right? How come the sum of the powers from both lists you get is the same? How come the pairwise sums you get from these lists is the same? And this is the magic of these Morse sequences. So I'm going to, at this stage, present. Yeah, I know, right? So I'm going to present a proof for both of these things. I will say these proofs are about as magical as the actual facts, but you will walk away with some justification as to why it's actually true. So hope everyone is excited to see the actual arguments as to why this is true. So in order to get set up, I want you guys to observe some things about these sequences, okay? These sequences are defined recursively, right? So, for example, you have, so the way I've done things, for example, you have, didn't mean to scroll there. So, for example, you can look at let's take a look at A2, okay? It's just 1, 2. And let's take a look at B2. Okay, 0, 3. So A2 is 1, 2, B2 is 0, 3. I'm just gonna write that down real quick. So, A2 is 1, 2. B2 is 0, 3. Okay? Just want you to look at that. Now I'm gonna write down what A3 is, and then I want you to look at what B3 is. Okay, so A3 is 1, 2, 4, 7. B3 is 0, 3, 5, 6. Okay. 1, 2, 4, 7. B3 is 0, 3, 5, 6. Wait, what did I write around? 0, 3, yeah, 0, 3, 5, 6. Okay. Do you notice anything interesting here? Well, look at this. So look at how A3 and B3 can be obtained from A2 and B2. And this is very similar to the way this Morse sequence is obtained originally, right? So for example, you can look at A3 and notice A3 splits as 1, 2, and 4, 7, right? So 1, 2, union 4, 7, okay? And then also notice that B3 splits as 0, 3, and 5, 6, okay? Okay. So in order to get the next piece, you definitely start out with the previous piece. I mean, I hope that part at least makes perfect sense, right? So to get the next piece, you use the previous piece. So A3 contains A2 at the start, right? And B3 contains B2 at the start, okay? Hopefully I'm not blowing anyone's minds here. This is hopefully perfectly reasonable. But I want you to notice something, that the piece that you add is actually the appropriate power of 2 plus the other one. So 4, 7, if you think about it, right, is just 4 plus 0, 3, okay? And 5, 6 is just 4 plus 1, 2, okay? Does that make sense? So you take the previous one, and then you take the other one, and then you add the appropriate power of 2, okay? This is the key fact that we're going to use in our recursive or inductive proof as to why these have all of these like insane magical properties, okay? So let's check this one more time and check it for the big one that I've written up top, okay? So for example, A3 and B3 are like this, right? So these are A3 and B3. I'll put them up top. All right, so far so good. But now let's take a look at A4 and B4. So A4 starts out the same way A3 starts with. So it starts with a 1, 2, a 4, and a 7. But then the things that you add on are 8, 11, 13, and 14, which you'll notice are exactly 8 plus whatever B3 was. So you add on 8 plus whatever B3 was. So 8 plus 0, 3, 5, 6, right, is actually equal to precisely 8, 11, 13, 14. You see that? So there's some weird, kind of interesting, surprising, fun recursion going on here, right? Okay, so hopefully that part of it makes sense, okay? Now I'm gonna say something else. Okay. Let's say we knew this is true, Okay, so for example, if I take a look at, you know, how's my notation working right now? So it's A4 and B4, right? So for A4 and B4, right? What is this saying, right? So basically, this is saying that, you know, if I take any of the elements of A4, right? If I take the entire list A4, and let's say I take the like ith element of A4, and then I raise it to some power k, so, you know, and then I add all these up, right? As I goes from, you know, this would be 1 to whatever the length of A4 is, it'll be 2 cubed, right? This thing should equal the sum I goes from 1 to 2 cubed B4, right? The ith element raised to the kth power. This is literally what I have up top over here, right? I'm saying the exact same thing. So this will work as long as, you know, k is less than 4. That's the only restriction here. You know, I definitely need k to be less than 4 in order for this equation to hold. So, you know, here I do need k to be less than 4. We already know for a fact that it does not work. It does not hold if k is equal to or greater than 4. Okay. So in general, what do we have over here? If I were to write it down, what I'm dealing with here, it's the following. If I take all the terms in like an, right, and I add them all up, how long is an? An has a length 2 to the n minus 1, right? And I raise these to a kth power. This should always equal, right, if I add up all the terms in bn, right, to the kth power. And once again, this only works as long as the powers that I'm raising to are less than n. Okay, once again, I hope this makes perfect sense. This is just me writing down a generalization. Okay, but I want you to notice something. So I know that, for example, let's say you take as a given what I've written so far, okay? Let's say you take as a given, let's say you accept all of these equations. Then actually a stronger equation is true, isn't it? So this is saying, you know, if you take all the elements of an, you raise them to some power, you'll get the same thing on the other side, right? But if this is true, you can actually apply any polynomial on either side and get the same answer. So for example, let me take my favorite polynomial of degree up to 3. Let's say my favorite polynomial in the world is n squared plus 6n plus 1. Okay? Let's say this is my favorite polynomial in the world. Then what I can do is I can plug all the terms of an into this polynomial and add them up. Or I can plug all the terms of, let me be more specific. I can take all the terms in A4 and plug them into this polynomial and add them up. K less than n, did you mean k less than 4? The second time I meant k less than n because I was writing the most general version, right? So for example, if you look at, where'd it go? So for example, if you look at A6 and you can raise it to the 5th power and add them up, that's the same as B6 if you raise it to the 5th power and add them up. So all that you really need is that the power you're raising to be less than n, less than the like n that you're using to construct the list. I hope that makes sense, Ken. Let me know if there are any questions about that. Okay, so here's the thing. I can take all the elements of A4 and plug them into this list, plug them into polynomials and add them up, right? Or I can take everything in B4, plug them into this polynomial, and add them up. I should get the same answer on either side. Because let's think about what plugging into this polynomial is and adding them up is doing. That would be just adding up all the squares, adding up 6 times all of the numbers, and then adding 1, adding 1 8 times, right? Plugging B4 would be the same as adding all the squares, adding 6 times all of the terms, plus adding 1 8 times, right? So actually, if this is true, in fact, more is true, right? You can actually take your favorite polynomial, as long as the degree of that polynomial is less than n, right? So say you have your favorite polynomial, f, right? And let's say f is a polynomial. Okay, and let's say the degree of f is less than n. Okay, then here's what you can do. You can just take everything in an, right? Take everything in an and just add up f of a. It'll always be the same as taking everything in bn and adding f of b. The claim that I made before should be the same as this claim that I'm making here right now. Okay? I hope that that makes perfect sense. If it's true that all the powers work, then it should be true that all polynomials work, right? I'm not saying anything different. It's just that thinking about it in terms of polynomials turns out to be a bit easier than thinking about it in terms of all of the straight powers. Okay, so I hope that that makes sense. So this is the claim here that I'm going to actually try and prove. So I'm going to try and prove this. Okay, so the idea is that, I'm plugging in all the terms in A in a polynomial and adding them up, plugging in all the terms in a Bn in a polynomial and adding them up, and the claim is that I should get the same thing on either side. Okay. Why does thinking about it like this help me at all? Well, I'm going to prove this by induction. Induction is just a type of recursion. We're going to start with the most basic case. We're just going to induct on the degree, so we're going to look at the degree of f. Okay. So we're going to start off with the smallest degree. So what I'm going to do is I'm going to look at the degree of f. Okay. So first and foremost, I'm going to start with f having a degree of 0. So I'm going to start with, the degree of f is 0. Okay. If the degree of f is 0, then I'm just going to be adding a bunch of constants. And then this will always work. So if the degree of f is 0, then f is a constant, right? And then, for example, if I'm adding up, plug all the terms in an into... Right. F, that's going to be the same as if I plug all the terms in Bn into F, right? Because essentially, this is just going to equal... The left-hand side is just going to equal, add up all the constant terms in this polynomial as many times as there are terms in an. And the right-hand side is going to be, add up the constant terms in f, however many terms there are in Bn, but we know that the number of terms in An and the number of terms in Bn are the same, so it does work out in this case. Okay, so I hope that that makes reasonable sense, but let me know if there are any questions about it. So if f is a degree 0 polynomial, then you can definitely compute f of a for all the terms in An and compute f of b for all the terms in Bn, and you can add them up on either side. You should get the same thing either way. Okay. So what happens for higher degree terms? Okay, so let's say we already know that it's true for a... So let's say we've already figured it out for a polynomial of degree n, or I'll say k. Let's say we've already figured it out for a polynomial of degree... Actually, I've used k before too, so I'll say r. So to do the recursion or to do the induction, I need to figure out, so how do I reduce the case of it working for a polynomial of degree r plus 1 to it working for a polynomial of degree r? Okay, so you assume it works for a polynomial, right, of degree r. Okay. If you knew this, can you use this to make it work for a polynomial of degree r plus 1? So can we So I shouldn't say a polynomial. So assume it works for all polynomials of degree r. All polynomials of degree r. And then so can we make it work for all polynomials of degree r plus 1? See, if you can do this, then you can ladder all the way down. See, if you can make it work for, if you can make it work for 8 if you know it works for 7, then you can use the same logic to make it work for 7 if you know it works for 6. 5, 4, 3, 2, 1, 0. That's how induction works. Okay. So for now, let's say I hand you a polynomial of degree k plus 1. Okay, oh, sorry, r plus 1. So say f is a polynomial of degree r plus 1. Okay. Do the following. You can define a new polynomial g of x, right, like this. Let's say g of x is f of x plus, let's say, 2 to the, f of x plus 2 to the n minus f of x. Okay, so let's say f is a polynomial of degree r plus 1, right? Define g of x to equal f of x plus 2 to the n minus f of x. Okay, let me know if that makes sense. Okay, so now we have g of x equals f of x plus 2 to the n minus f of x. All right, so what can we do with this? I want you to notice something about this polynomial. The leading term of this polynomial is the same as the leading term of this polynomial. So these have the same leading terms. Interesting, right? These two have the exact same leading terms, okay? So their difference should have no leading term, right? So their difference is going to be a polynomial of degree r, okay? So g has degree r, or at most r, I should say. Maybe more cancellation happens, I don't know. But its degree is at most r, okay? So if these have the same leading terms and I subtract them, then g has degree at most r. G having degree at most r, we can assume that the identity works for g. So I know for a fact that if I take all the terms in an and plug them into g, I should get the same thing as if I were to plug all the terms of bn into g and add them all up. Okay? So that's what we know. So just I'm going to keep the definition of g up here. So g of x has a degree at most r. It cannot have a degree bigger than r, right? Because its degree is less, we can say that, you know, if I plug all my terms into g, right? So I take everything in an and plug it into g. That's going to be the same as if I add up, I take everything in bn and plug it into g. Okay, so hopefully that makes sense. This is by recursion or by induction, if you will. But now I want you to remember something. The terms in an can be broken up into, well, actually, let me write this out. So remember, gx is equal to this, so I can just do this. So this is going to equal, take all the terms in an. We're doing f of a plus 2 to the n minus like the sum for all a's and an, right? F of a. And that's going to equal, add up all the terms b in bn, f of b plus 2 to the n minus the sum of just f of b, bn, bn. Okay, so let me just make myself a little bit more room. This is where we're at right now. Move this over a little bit just so it looks nicer. So this is the sum that we are at right now. This is what we are attempting to prove, okay? But I want you to notice something. I can take the negatives and put them on the other side. So for example, I can write this as the sum b in bn f of b, right? So I just put this on the other side, plus the sum a and an f of a plus 2 to the n, okay? And this is going to equal the sum, I'm putting this on the other side, so this is a and an, right? F of a plus the sum b and bn f of b plus 2 to the n. Okay, so let me shrink this a little bit just because I'm running over my own chat box, so just a little bit smaller. Save a little bit of room. Just let's see here. Okay, I think that's a little bit nicer. So now we have this. But do you guys remember that the way you get an plus 1, how do you get an plus 1? The way you get an plus 1, right? The way you get an plus 1 is you take an and to that you add bn, but to every term of bn you need to add a 2 to the n. Remember that? So actually this left-hand side is equal to exactly the sum of everything in bn plus 1 f of b. How crazy is that? And the right hand side is just going to equal the sum everything in an plus 1, because remember, how do you get b? How do you get bn plus 1? You just take everything in bn and then you take everything in an and add 2 to the n to it. F of a. So that's it. That actually completes the induction. So I don't even know what to say about that. I think that that's quite a remarkable and it's a lovely proof. I'm not sure who it's due to. Though I can give you the source, I think. I'm not sure where I got it, but it's somewhere on my computer. If anyone really wants to know, I can put it in the comments. But let me know if there are any questions about this argument. So essentially, you prove that this is going to equal this for any polynomial. Okay, I'm happy you liked it, Marsan. Okay, so there's that. Now, there's a second fact here that we were trying to prove, which is that, never thought the proof will go through such a different route. Yeah, I mean, there are other ways to prove it, but this is the nicest one that I found. So, I mean, it's really quite magical. So, what about this other fact? this idea that if you do, that's okay. Don't worry, the VOD will be posted. So what about this other fact about these? What about the fact that the pairwise sums of these sequences are all equal to each other? In fact, what I'm going to do is I'm going to prove something even stronger. So, not stronger, but at least more interesting. So here's what I want you to do. Imagine you construct the infinite Morse sequence. Okay, so it would be like 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, and you just keep going forever. Okay. Well, I'm happy you liked it. Replica clipper. Thank you. Okay, so here's what I want you to imagine doing. So I want you to imagine taking such a sequence and just making it go on forever and ever more. So you just extend this infinitely, and so it goes. 1, 0, 0, 1. 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1. This will give you a partition of the integers into two pieces, right? If you keep this going forever, you can just take, not the integers, sorry. It'll give you the partition of the whole numbers into two sets, right? One set will look like, 0, 3, 5, 6, 9, 10, 12, 15, and so on forever. And the other set will look like 1, 2, 4, 7, 8, 11, 13, 14, on forever. Okay? So here's what I'm going to try and prove to you. And this is going to be another one of those like magic insane proofs. Okay? So what I'm going to try and prove to you is that the property that I was describing holds for these two infinite sets. Okay? So for example, you can write 8 as 3 plus 5, right? So let me circle it. So you can write, so pick your favorite number. Okay, pick your favorite number. Let's say my favorite number is 8. You can write 8 as 3 plus 5, right? So there's one way to write 8 as a pairwise sum in this first sequence. I do not see any other way to do it. The only way to write 8 as a pairwise sum in this first sequence is using 3 and 5. And so that means there should be exactly only one way to write 8 as a pairwise sum in this second sequence. So this would be 1 and 7. Okay? Let's pick another number. How about I want to pick something that there are two ways to write. I can actually just cheat. So there should be two ways to write. Is there a good one? Maybe. How about 15? Okay, let's do 15. So how many ways are there to write 15 as a sum of... You would rather I do a prime? Okay, I wanted to do one you can write in multiple ways. So how about... I don't think there are any primes in the list that I've given that can be written in more than one way. So let me just do 15 and then I'll do a prime. All right. So let's think about 15. So 15 you can write as 0 plus 15 in the first list, right? You can also do, I see a 3 plus 12 in this list, and I also see a 5 plus 10 in this list, okay? So what about from the other list? Well, notice you can also write 15 as 1 plus 14. You can also write it as 2 plus 13. And then you can also write it as 7 plus 8. Let me see if I'm missing something. Oh yeah, you could have also written it as 9 plus 6 in the original list. And so you can also write it as 4 plus 11 in the second list. Okay, so let's see here. I think that that's everything. And you notice the number of ways to write 15 as a pairwise sum in the first list winds up equaling the number of ways to write 15 as a pairwise sum in the second list. Okay, So there's another really weird and surprising property here. Kind of shocking. Why? What is going on here? The only proof that I know of this is a very kind of a very sneaky, very tricky, sneaky kind of proof. So let's go through it and let me know what you think of it. If it gets too advanced, I can stop. But the idea is to use generating functions, actually. So let's say you have a sequence, right? So in our case, our sequences, I'll call the sequences A and B. These are our mega sequences. So we'll say A is the one that goes 1, 2, 4, 7, 8, 11, 13, and so on. Okay? And let's say B is the one that goes 0, 3, 5, 6, 9, 10, 12, 15, and so on. Okay. So here's what I'm going to do. I'm going to define a polynomial. Okay? I'm going to define an infinite polynomial using the A's. So here's how I'm going to do it. So the polynomial that I'm going to define using the A's, actually this is going to be a generating function, so it's going to be an infinite polynomial. If you don't know anything about generating functions, you can think of this maybe kind of like a Taylor series. But I'm going to define AX as follows. AX is going to be x to the 1 plus x squared plus x to the 4th plus x to the 7th plus x to the 8th, and so on. Okay. Let me know if this is going to get pretty wild. So let me know if that makes reasonable sense. Okay. And now, similarly, you can define bx. So bx would be like 1 plus x cubed plus x to the 5th plus x to the 6th plus x to the 9th plus x to the 10th, and so on. So basically, I took the terms and I turned them into exponents. That's the conversion I'm doing to turn these sequences into generating functions. Okay. Hopefully that makes good sense. There's a few things I want you to notice about this. If I look at AX and I add it to BX, what's going to happen? Well, I'll get everything, right? I'll get 1 plus x squared plus x cubed plus x to the 4th, which is everything. Agreed? And if you remember, this is just the expansion for 1 over 1 minus x. Okay? So it's because ax plus bx has every exponent of x included in it. So remember, ax and a and b were partitions of the whole numbers. So if you add ax and bx, you should get everything. Okay? So you have this. All right, now we know something interesting about ax plus bx. Ax plus bx is 1 over 1 minus x. I'm just going to put this in a corner in case we need it later. All right, so far so good. We would like to study all of the possible pairwise sums from A and all of the possible pairwise sums from B. Okay? So we would like to study all of the pairwise sums from A and all of the pairwise sums from B. Okay? What are all the pairwise sums from A? So the pairwise sums from A are like 1 plus 2 and 1 plus 4 and 1 plus 7 and 1 plus 8, but also 2 plus 4 and 4 plus 7 and 7 plus 8. So it kind of feels like what I should be doing is I should be kind of squaring AX, right? Because if I square AX, it's like I'm multiplying x1 plus x squared plus x fourth plus x to the 7th, multiplying it with itself. Okay? So, and notice when I do this, I get something very close to what I want. So for example, this contains this term. Let me use a different color pen. So for example, this will contain x cubed because I'm multiplying x to the 1 with x squared. So this contains an x cubed. But notice I'm also multiplying an x squared with an x to the 4th. So this will also contain like an x to the 6th. And for example, I'm, So for example, this thing does contain all of the pairwise sums. It actually contains all of the pairwise sums twice, because I can do x to the 1 x squared, but I can also multiply it this way. If I'm like kind of, you can imagine foiling it out. So this will be another x cubed. This will be another x to the 6. So you'll get all the pairwise sum terms, but you see them all appearing twice. You see them all appearing twice. Another annoyance here is that I get the same term added with itself. So for example, you'll get from here, x to the 1 multiplied by x to the 1, you'll get an x squared that you do not want. And you can also multiply this x squared with this x squared, which will give you an x to the 4th that you do not want, okay? So what I would like to do is get rid of all of these terms that involve multiplication of a term on the top with a term on the bottom. Because remember, what I'm after is like sums that come from things that are pairwise distinct. And you'll notice the exact formula that you need is just going to be as follows. So it's just going to be, you want to get rid of all the things that involve multiplication with themselves. And so you can do this thing where you just subtract off ax squared. If you plug in x squared, so if you plug in x squared, that's like multiplying all the exponents by 2. So that's the same thing as looking at everything multiplied with itself, okay? Then you multiply it by half to get rid of the 2's, and you have what you need, okay? So this function will look like this. It'll just look like, you know, like you're adding, you know, if like a1 and a2 are in A, it's like you're just adding all x to the a1 plus a2. Because as long as a1 is not equal to a2, because I got rid of all the a1 equals a2 things by subtracting off the ax squareds, okay? And you would get 2 of these, but I'm dividing by 2, okay? So this is the generating function that is describing everything that can be written as a pairwise sum from A. Okay? Let me know if that makes sense or no sense whatsoever. Okay? So this generating function is describing everything that can be written as a pairwise sum from A. Agreed? So what am I claiming? I'm saying everything that can be written as a pairwise sum from A is the same as everything that can be written as a pairwise sum from B. So actually, the only claim that I'm really making here, all I'm really saying is that this function is in fact equal to this function. YouTube thumbnail is showing the previous stream. Uh-oh. Well, I don't know if I can edit it right now. Okay, that's unfortunate. I kind of like my thumbnail for this stream, but oh well. I assume YouTube will fix it eventually. All right. Regardless, saying that the pairwise sums from A and the pairwise sums from B are the same is the same thing as saying that 1/2. So that this, it's basically saying this identity. Okay. So I'm just going to put this up top, and now we're going to examine this more carefully. So what does this mean? Well, I can cancel out the halves, right? And now I have this. I have basically that ax squared minus bx squared is in fact equal to, let's see here, ax like squared on the inside minus bx squared on the inside. Okay, but here you on the left hand side you can use that factorization. A squared minus b squared is a plus b, a minus b, right? So this is just equal to ax minus bx times ax plus bx. But remember earlier we managed to figure out that ax plus bx is 1/1 minus x. Okay? So in fact, I get this. Interesting. Okay, hopefully that makes reasonable sense. But notice this identity is recursive. ax minus bx equals 1 minus x times ax squared minus bx squared works no matter what x is. So I can use this identity again over here. So this becomes 1 minus x, 1 minus x squared times ax to the fourth minus bx to the fourth. But of course, since I was able to do this again, I can do it one more time, and I can just keep going on forever. So essentially, the identity that you get is the following. One minus x, 1 minus x squared, 1 minus x to the fourth, 1 minus x to the eighth, going on forever and evermore. Okay? So, interesting, right? So, what does this mean? So, what happens when you now multiply out the right-hand side? Okay? What's going to happen here? So, you get for example, when is this going to, so you can think about multiplying this out, and then you can think about when is the coefficient of x to the n going to be positive and when it's going to be negative. And so this is going to be basically, so for example, you'll get a 1 for multiplying all the ones, right? But this is going to be essentially like, I don't even know how to write this appropriately. So for example, you'll get x to the n when n is the sum of an even number of powers of 2, right? Because that's then the negatives will all cancel each other out, right? Even number of powers of 2. And you'll get negative x to the n whenever n is the sum of an odd number of powers of 2. That's what multiplying this infinite product looks like. Does that make sense? At least I hope so. Okay, so if you multiply the sum on the right, you'll just get x to the n whenever n is the sum of an even number of powers of 2, and you'll get negative x to the n whenever n is the sum of an odd number of powers of 2. But let's think about that for a second. So we know that for a sequence A and B, right? For A and B to have the exact same pairwise sums, the following identity has to hold. We already thought about this. It's like ax squared minus a x quantity squared must equal 1/2 bx squared minus b x squared, right? And what about the residue? Yeah, so basically the starting term of ax to the 2n, so it'll be ax2 to the n, right, minus b x2 to the n. So as you'll see, the first term of this, the first power of x that appears in this keeps getting larger and larger and larger, right? So it vanishes if you just take n to infinity, okay? So the first, you can just think about what the earliest term of x appearing in this sequence is going to be. So in this function is going to be. And you'll notice that that first power of x that appears is going to keep getting larger and larger and larger, which is why it vanishes when you take it to infinity. So I hope that answers your question. Anyways, so putting things aside, this is all that needs to be true for any partition of the whole number. So you start with, let's say A is a partition of the whole numbers. I'm sorry, let's say A and B split the whole numbers in two, right? Then in order for the pairwise sums to be the same, this needs to be true. But we were able to derive from that, you know, AX minus BX is equal to, you know, this is like a big sum that has x to the n when n is the sum of an even number of powers of 2. And negative x to the n when n is the sum of an odd number of powers of 2. But what is that telling me? Remember, ax will have all the positives and bx will have all the negatives. So this is in fact telling me that ax is the generating function, right? So this is just telling me that ax is the sum of x to the n, when n is the sum of an even number of powers of 2. And bx is the sum of x to the n whenever n is the sum of an odd number of powers of 2. Okay? But now I want you to re-examine the Morse sequence from the start. And I'll leave this to you as an exercise, but it is indeed a fact. Let's look at this. What was the Morse sequence? It was 0, 3, 5, 6, 9, 10, 12. 0 is just the sum of no powers of 2. So this is the sum of 0 powers of 2. 3 is 1 plus 2, which is the sum of 2 powers of 2. 5 is the sum of 1 and 4, which is the sum of 2 powers of 2, right? 6 is the sum of 2 and 4, which is the sum of 2 powers of 2. 9 is 1 and 8, which is the sum of 2 powers of 2. 10 is 2 and 8, which is the sum of 2 powers of 2. 12 is 4 and 8, which is the sum of 2 powers of 2. Right? So another way of thinking about the sequence that we've been constructing recursively is just on one side is all the digits that have an even number of ones appearing in their binary expansion, and on the other side is all the digits that have an odd number of ones appearing in their binary expansion. So if you start out with this identity, right? If you start out with, oh, I'm out of undos. So if you start out with the identity that says that your partition has the same number, like the mixed sums are exactly the same, you get that one part of the partition has to have that there are an even number of ones in the binary expansion of n, and the other side will get that there have to be an odd number of ones in the binary expansion of n, which is precisely the Morse sequence, and we are done. And that's it. So let me know if there are any quick questions about that, and after answering them, I'm just going to end the stream. So let me know if there are any questions about that. I was very happy to share this with you, including some of my hideous Mathematica code. All right, but if there are no more questions about this, I guess I'll end soon. Let's see here. How long have we been going? Like an hour 15. I think that's probably a good time to quit out of a math stream. All right. Holy crap, amazing. Thanks a lot. Thank you. I'm happy you enjoyed it, Ken. All right, I'm heading out. Thank you all so much for showing up. I really appreciate it. And I will be streaming again on Wednesday at 1 p.m. I'll be bringing the heat with more insane, weird, still relatively elementary mathematical facts. And I hope you enjoyed this. All right, I'm gonna head out now. So peace. Thank you so much.